Before diving into the supernova, we must first answer the question, what is a supernova? A supernova can be defined as when a high mass star explodes. It is literally the largest explosion in space because of the change in the core of a star. Supernova explosions can outshine entire galaxies for weeks, and it is literally the brightest explosion in our universe. Supernovas are actually extremely rare. They only occur about 1 in 400 years in our galaxy, and in other galaxies similar to the Milky Way, they occur about every 1 in 50 years. Secondly, we can move into what causes a supernova. Supernovas occur when older massive stars can no longer go under nuclear fusion, which leads to gravitational collapse. This collapse heats up and pushes out the outer layers or the outer shells of a star, causing explosion. Lastly, we can look into the remnants, what's left over after a supernova occurs. The energy released in the collapse of the core leaves the outer layers of the star into outer space. Supernovas break down into two types. As you can see on the left, we have type 1, which breaks down into three subtypes. Type 1A, type 1B, and type 1C. It is caused by a binary star system. When you look on the right, you can see type 2, which breaks down into two subparts, type 2L and type 2P. This is caused by gravitational effects. Here's a diagram to give you an overview of the processes that a type 1 star versus a type 2 star has to go through in order to evolve into a supernova. First, let's look into type 1 supernovas. They must be in a binary star system where two stars orbit the same point. Runaway nuclear reaction ignites one of the stars in the system, which in turn white dwarf stars steal matter from the companion star. Inevitably, getting too much matter causes the star to explode. Now let's look into the subtypes of type 1s, A, B, and C. There's also a diagram on your right hand side to help guide you guys along. The process of a type 1 supernova first originates from a white dwarf in a binary star system. Secondly, the white dwarf absorbs gas from the other star, the companion star. Third, the white dwarf compresses. Fourth, it sets off a runaway nuclear reaction inside of the core. Lastly and fifth, it creates a cataclysmic supernova outburst. Also, one thing that only applies to 1A supernovas is there is a lack of hydrogen signature. Looking into type 1b and type 1c, they are like type 2s and they collapse but loss of a outer hydrogen envelopes. Also, when looking at type 1s, the companion stars are usually extremely hard to locate. Moving into the second type of a supernova, a type 2. Type 2s must be 7 times bigger than the Sun, about 8 to 15 solar masses. Type 2s occur when the core runs out of helium and hydrogen, but still has enough mass and pressure to fuse carbon. The process of type 2s follows as first, heavier elements build up at the center of the core. Secondly, after star's core is heavier than the Sunday-Trusker limit, which is about 1.4 times the Sun's mass, it starts to implode. Third, the core heats up and becomes dense. Fourth, implosion bounces back off of the core, expelling stellar matter into space, which then forms a supernova. It also leads a neutron star. Breaking type 2s into subcategories. The subcategories are based upon the light's curve. The light in type 2Ls declines steadily after the explosion, versus the light in type 2Ps that stays steady for some time. Both have hydrogen in their signature, and by the explosion in the supernova, it creates a vibration like giant speakers and emits audible hums. When a star is 20 to 30 times the sun's mass, it actually forms a black hole. You can also look on your right hand side to get a detailed diagram. Lastly, let's look at the molecules in a supernova. The core pressure cancels because of electrons and protons that make neutrons and neutrinos. The neutrons then collapse to the center, leaving a neutron star. The electrons inside of core speed up to the speed of light, which is extremely energetic. Iron is also at the core of a supernova, and everything higher than iron on the periodic table comes from a supernova. Here is a video by Discovery News to help you guys review and preview the information given to you so far. Press the link to check it out.
You guys, the star is exploding right now up in the sky. You can see it with regular binoculars. Look for it. Holy crap. Sorry guys, got a little carried away. I'm Trace. This is our weekly D-News Space Update. Thanks a lot for tuning in. So, if you like space news, you've likely seen stories about M82's supernova. It's pretty exciting, although not entirely unexpected. The cigar galaxy M82 is known as a starburst galaxy because it produces so many stars. It was in the news back in 2009 when a new formation began throwing radio waves in every direction. Scientists were baffled. Basically, M82 is cool. The stars of M82 are on a short life cycle, coming into being and then dying rapidly, so supernovas should happen every 20 to 30 years. As M82 is about 12 million light years away, these supernovas occurred about the time ants, horses, and snakes began evolving to frolic on Earth's new grasslands. We're only seeing these short-lived stars now because it took so long for the waves to reach Earth. A supernova is part of the natural life cycle of a star, but not all stars or supernovae are created equal. The giant fusion reaction that we call a star must contain a balance of gravitational mass to hold together and an explosive force so they don't collapse. There are two general types of supernova. One type can be triggered by a white dwarf, which is the ancient husk of a burnt-out star. It sucks so much gas from a binary companion star that the balance is tipped and it collapses and explodes. It needs about 1.4 times the mass of our sun to do this, of course. Another type of supernovae is caused by the violent death of a massive star. When the star runs out of fuel for fusion, then the balance tips the other way and the star suffers a core collapse. But that isn't what caused this supernova, however. This one was a type 1a supernova. When the white dwarf explodes, it does it very predictably, creating an identifiable level of brightness. Because of this, type 1a supernovae are called the standard candles of the cosmos. Astronomers can use them to measure the distances between galaxies and help us measure things like the scale of the universe and the effects of dark energy. So when M82 was spotted, astronomers got pretty excited, to say the least, especially because it can be seen with regular old binoculars. This is the closest supernova since 1987 and the closest type 1a supernova since 1972. If you'd like to watch an ancient white dwarf from your backyard, grab your spyglass and head to a dark location. The farther from other light sources, the better. First, find the Big Dipper, called Ursa Major, and use the two endpoints of its pot to draw a line to Polaris, the North Star. That's also the tip of the handle of Ursa Minor, the Little Dipper. Then, backtracking to the approximate halfway point of the two Ursas, you should see M82. It won't reach maximum brightness for a week or two, so you've got some time. For more stargazing tips, check out the links down in the description, and if you need any supernova help, talk to my friend Dr. Ian O'Neill over on Twitter at AstroEngine. He helped me a bunch with this weekly D-News Space Update, so thanks a lot for that. And if you spot the supernova, be sure you let us know. Thanks for watching, everybody. Subscribe for more videos. Bye.
So, how do scientists search for supernova? One way is through the illumination method. As stated before, type 1 and type 2 supernovas especially get extremely bright, then fade over time, which reveals its true brightness. By comparing a star's true brightness to how bright it appears, astronomers can calculate the distance. Then, with the distance, astronomers can measure how fast the star is moving away from the Earth by measuring its redshift. With this redshift, scientists can detect the flare of a supernova. Some astronomers use automated small telescopes to survey the sky on different nights and compare the images to detect the flare. Once supernovae are spotted with smaller telescopes, we can use even bigger telescopes to examine them. The Hubble Space Telescope and the Chandra X-ray Observatory have captured great photos of supernovae. The New Star mission is the future of examining supernovas. It was launched in 2012. It is the first orbiting telescope that focuses light in the high-energy region of the electromagnetic spectrum, and it will search for the remnants of supernovas, collapsed stars, and black holes.
Why do we study supernovas? Supernovas prove that the universe is expanding. Astronomers measure the speed of the star as it moves away from the Earth by determining its redshift. As quoted by hexdex.org, if a supernova is 1 billion light years away from Earth, it exploded 1 billion years ago. This allows scientists to determine the speed in which the universe was expanding during different periods of its history. Supernovas create elements that are scattered across the universe and that can collect and form new stars or planets. During the Big Bang, helium and hydrogen were the first elements created. These elements cooled, forming clouds that would later create stars. All elements found on Earth were created in the center of a star. In 1995, astronomers found supernova Champagne that reached up to 2 solar masses. This gave way for scientists to predict how other supernovas would affect the universe. Since scientists understand how supernovas die, they use this knowledge to predict future events in the universe as well as hypothesize about what happened in our universe billions of years ago. Astronomers discovered that 1A supernovae leave behind debris and are the reason as to why there is so much iron in the universe.